everyone. So I want to take a look at this related rates worksheet. Um, and it's 8 problems. I will say that number 6, don't freak out. Okay? All right. I also want to say number 1 is difficult for some people, even though it's supposed to be not so bad. So let's take a look at one now. A spherical balloon is being inflated. As the radius of the balloon increases, there's a corresponding increase in volume. Okay, so we're thinking about volume, and we're thinking about its connection to radius, and we've already heard about a change in volume depending on a change in radius, right? That's what I read in that second sentence. As the radius of the balloon increases, there's a corresponding increase in the volume. So there's a relationship between the change in volume and the change in radius. Find the rate of increase of volume when radius is 3. Okay, so we want to find when r is 3, and are these feet? I don't see anything that says feet, but my answer here says feet. So we're going with feet. Okay, big balloon. So this is not, however, with respect to time, and this is important here. That second sentence says, as the radius increases, there's an increase in volume. Not as time passes, there's an increase in volume. Right? That would be dV/dt. There's a change in volume that depends on a change in time. No. And while often when we do related rates problems, we are taking the derivative with respect to that parameter called time, here, no, not so important. Here it's just with respect to radius. And I think that's why a lot of people struggle with this problem. 4/3 pi r cubed is the formula for volume of a sphere. And now when I take the derivative of both sides, I'm not going to take the derivative with respect to time. I'm going to take the derivative with respect to radius. d dr. d dr 4/3 pi r cubed. And so here I get dv dr. And then over here, I bring down that 3, and I have 4 pi r squared. Now, you could always think about this as chain rule and say, okay, I took the derivative of the outside, and I left the inside alone, but now I have to come back and take the derivative of the inside with respect to radius. And that's going to be dr, or 1. So all I'm going to do is plug this 3 in here, and I'm going to get that dV dr is 36 pi cubic feet per foot, right? It's not minutes or seconds here. This isn't about time. This is about the volume is changing by 36 pi cubic feet for every 1 foot increase in radius when r equals 3, okay? And I guess that's one of the reasons why I don't like that simplifying that many of you like to do, where we talk about acceleration as meters per second squared, because that doesn't make sense. And here, tell me what the hell this is. 36 pi square feet. What does that mean? How is this change in volume with respect to radius going to be an area? Yeah, that doesn't make any sense to me at all. But I do understand this as, oh, look, my volume is going up by 36 pi as my radius is going up by 1 foot. Okay? So, yeah, this one, the answer is there. 36 pi cubic feet over foot. And sure, you could certainly turn it into that, but I don't know what the hell that means. I don't know. And maybe someone will tell me. Okay, Now, though, we move back to time, and we will see time in all the rest of the problems we have here on this worksheet. Okay, a point moves on the parabola 6y equals x squared in such a way that when x equals 6, the abscissa, that's a great word, isn't it? I just had to bring it out for you. Abscissa. The abscissa is increasing at a rate of 2. The abscissa is increasing at a rate of 2 feet per second. 2 feet per second. I wonder what abscissa is. Any of you know? It's been so long since I ran into a student who was able to tell me what an abscissa was. Well, it turns out there's abscissa and its dear friend, ordinate. I know. How could you not know those words? Well, it turns out that the abscissa is the x value, and the ordinate is the y values. The y value. And so when we think about ordered pair, it's abscissa, comma, ordinate. When we think about coordinates, together, these make our coordinate. And so here, instead of writing something ridiculous like abscissa, I'm going to say that dx dt is 2. Okay, that's what we're meant to understand there with the abscissa changing at a rate of 2 feet per second. Okay, what is the rate? At what rate is the ordinate increasing? And so now I know that we're looking for dy dt. So let's take the derivative with respect to time. I'll have 6 times, right? This is a constant times the derivative of this with respect to time. So I want the derivative of this with respect to time. And that's going to equal, I have to take the derivative over here with respect to time. I take the derivative of the outside squaring. I get 2, leave the inside alone, times the derivative of that inside, derivative of that thing inside called x, with respect to time. Okay? Now, I'm looking for this, which means I must know that and that. Oh, look, x equals 6 and dx dt equals 2. So we've got 6 dy dt equals 2 times 6 times 2. And don't forget you want dy dt, or the change in the ordinate, all alone. So I end up with 4 feet per second when x equals 3. I'm sorry, x equals 6. Okay? What's next? 3. The bottom of a 20-foot ladder is sliding across the ground at a speed of 3 feet per minute. So here's my ladder, and I'm going to call this x, I'm going to call this y. And what did they just tell me? Well, at first they told me that the ladder is a constant 20 feet, but they also told me that this is sliding along the ground at 3 feet per minute. So I'm going to call that, I'm going to name that calculously dx dt. And I'm going to say that dx dt equals 3. Okay. Find the velocity of the top of the ladder by using implicit differentiation. Okay, so what we want to know is, as this thing is sliding out and this thing is sliding down, what is dy dt? Okay, so what relationship do we know between these objects? Well, we know the Pythagorean theorem. So we've got x squared plus y squared equals 20 squared. So the derivative here is going to be 2x dx dx plus the derivative here. Oh, wait. I'm sorry. The derivative of the inside with respect to time. Plus 2y dy dt equals the derivative of a number is 0. You may want to make a note to yourself if you had thought anything other than 0 there. So what do we know? Well, we know that dx dt is 3. So I can say 2 times 3 times x plus 2y times dy dt equals 0. I feel kind of stuck, though. Don't we have more? And the answer is no, we don't have more. That's all we've got. But what did the directions say? They just wanted us to say what velocity is. And my velocity is this rate of change in this distance with respect to time. So really all they want me to do is get this far and then get dy dt by itself. So I'm going to subtract 6x from both sides. I'm going to have 2y dy dt equals negative 6x. And I'm going to divide both sides by 2y. And I get dy dt equals negative 3x over y, which is the answer on the worksheet. And don't forget, of course, this is feet per minute. Okay? Sometimes we want the problem to be much harder and much longer than it is. No, not so much to do there. Okay, what's next? Number 4, a man is approaching a pole 70 feet high, from 75 feet high. It's a little vague there. Is the pole 75 feet high or the guy? So, guy. Okay, 75 feet high, walking at a rate of 3 feet per minute. What is happening? At what rate is he approaching the top of the pole when he is 100 feet away? Okay, so here's what I get from that sentence. There's a lot. First, I get that he's walking toward the pole. And I know that this guy, in fact, guy is here, not drawn to scale. I know that we're wondering about this, the rate of change between the guy and the top of the pole. So if I'm calling this x and I'm calling this y, I think I'm going to call this h today for hypotenuse. But usually I call it d for distance. Call it whatever you like. So we've got 75 feet high. He's walking at a rate of 3 feet per minute. So I've got that dx dt equals 3 feet per minute, right? That's the change in the guy. The guy is moving this way. But away, he's going toward the intersection. 3 feet per minute. Okay. At what rate is he approaching the top? So that says find dh dt when he is 100 feet away from the pole. So x equals 100. All right, do we have anything else? Oh, it's a 75-foot pole. That's a constant. Okay. What do you think? What can we do here? What do we need to do? I'm looking for dh dt. I've got dx dt. I'm trying to understand, do I have some sort of an equation that can relate x and h in this situation? That's right, this is Pythagorean theorem. We've got x squared plus y squared equals h squared. Now, y is not a changing quantity. And remember, things that aren't changing quantities, I plug in before I take the derivative, and things that are changing quantities, like this length being 100, that's a changing quantity. As he gets closer, x gets smaller. But this is staying the same. So we're plugging in the 75 here, and we're saying, okay, let's take the derivative with respect to, looks like time in this problem. So I've got 2x dx dt plus, and the derivative of this number, please say 0. Please don't bring the 2 down. Just say 0. And over here, 2h dh dt. I like dividing by 2 on both sides, and I like getting rid of this plus 0. So I need x dx dt, h in order to find dh dt. Okay, that's the thing I'm looking for, which means I know that, and I know that. Well, they told me x was 100, and they told me that dx dt was minus 3. But what about h? I don't feel like I have an h here. Oh, well, that's h, and that's 75, and that's 100. Oh. And do you really see that this is 3 times 25, and this is 4 times 25, and really we're just dealing with a 3, 4, 5 right triangle? So if this was 3 times 25 and this was 4 times 25, because I know of the existence of the Pythagorean triple 3, 4, 5, I'm going with 5 times 25 here for h, which is 125 times dh dt. So I'm going to just divide both sides by 125. I'll have 100 times negative 3 over 125 is dh dt. And I like to do some canceling here. This is 4, this is 5, and so I end up with minus 12 over 5, and these are feet per minute is dh dt. Okie doke. Okie doke. Let's move on. 5. 5 says water flows at a rate of 2 cubic feet per minute. Hey, cubic feet per minute, how would you name that calculously? dv dt. This is time. These are volume measurements. So I got a dv dt equals 2. Next, in the form of an inverted right circular cylinder. Inverted right circular cylinder. And by right, we mean like this, as opposed to, maybe I didn't even quite drive to it. So I expect to see something like that. Right circular cylinder or cone? Cone. As opposed to this sort of askew situation. Okay, we're not dealing with that. That's why they said right. They want us just to draw a regular cone here. So what about our regular cone? Inverted with an altitude of 2. So this is 2 feet. And a radius base of 1 foot. Okay. At what rate is the surface rising when the vessel is 1/8 filled? Okay, at what rate is the surface? So we've got this fluid, and we want to know the change in this, which I'm going to call h for height. We want to know at what rate the surface is rising when volume equals, when it is 1/8 filled. 1/8 filled. We're going to have to come back to that in a minute. I actually want to focus here now on setting this up because I think with this problem, when I think about the volume of the cone, volume equals 1/3 pi r squared h. I notice that I've been given a dv dt, and I've been asked to find how fast is the level increasing. I've been asked to find dh dt, which means I don't really want these r's. So I'm thinking in terms of similar triangles. All right, I know that this is 2 and this is 1, but here this is r and this is h. So I could say that 1 is to 2 as r is to h, right? Because I'm saying this is to this as this is to that. Or I could say something along the lines of 2 is to h, like whole thing, changing thing, as whole thing is to changing thing. And now when I cross multiply, notice what happens. Regardless of my setup, I get 2r equals h, and here 2r equals h by cross multiplying. So I've got a lot of freedom here to do what my brain sees, but now what I see is that r can be replaced with h over 2. And that's my helping equation for this. So let's plug in that h over 2. We've got v equals 1/3 pi h over 2 squared times h. So that's pi over 3 times h squared over 4 times h, or pi over 12 h to the third. Okay, that's my volume. And so when I take the derivative of both sides of this with respect to time, I get the following. I get that dv dt equals pi over 12 times 3h squared dh dt. Yeah? They told us that dv dt was 2. And we were told we were looking for dh dt. Well, I don't know h. And that's why this is important. Okay? I want to know when. I want to know what is the height when we have 1/8 the volume. Okay, so let's see what we can do about that. We want to know if volume is 1/3 pi r squared h. Oh, sorry. We already made that substitution. Was it pi over 4, pi over 12 h to the third? That's our volume formula. And we want to know what's height equal to when volume is 1/8 of its normal value. Well, what is the normal value here? They told us that the height of the cone was 2 and the radius was 1. So volume equals 1/3 pi 1 squared times 2. Okay, so volume equals 2 pi over 3. So what I want to know is, when is this equal to 2 pi over 3? And so if I multiply both sides by the reciprocal, multiply both sides by 12 over pi, I'm going to have h to the third equals 2 pi over 3 times 12 over pi. And I can do some canceling, and I end up with h to the third equals 8. And so I know that h equals 2. Oh. So the answer to the question is, wait, how can that be? Because I was 1/8. Where did my 1/8 go? Did I forget the 1/8? I did. Yeah. Okay, so this is the actual volume. I want to know when I have 1/8 of the actual volume. So if I multiply, sorry, it's just too messy, and your brains are probably not happy with me right now. So let's start again. They tell me that dv dt equals 2 cubic feet per minute. We know that this is 1 and that this is 2. This is r and this is h. And so we can say 2 raised to h as 1 raised to r and get 2r equals h. They've asked me to find dh dt. I don't have a dr dt. So I want to take this volume formula, 1/3 pi r squared h, and I want to get rid of the r's and replace with some h stuff. So I know that r equals h over 2. So then volume is going to be 1/3 pi h over 2 squared times h. And we said that means that volume is going to be pi over 12 h to the third. Now, what I'd like to do is say, okay, what's the volume of this whole cone? The volume of this whole cone is pi over 12 times h2 to the third. That's going to be 8 over 12, which is 2 pi over 3. So when full, the volume is 2 pi over 3 cubic feet. But I want, when is this thing 1/8 full? So let's think about 1/8 of the volume as being 1/8 times 2 pi over 3. And so these will cancel, and I'll end up with pi over 12. So volume is pi over 12. Remember, we had gotten to that place in our derivative where we said, okay, I know that dV/dt is going to be pi over 4h squared dH dt. And we were told that dV/dt was 2, but we got stuck over here saying, hey, I don't know the height, and I'm supposed to know the height because I'm looking for this thing. So what about that height? Well, they told me that I need to find the height when volume is 1/8 of its actual value. So I'm going to take this volume here and replace it with pi over 12. If I multiply both sides by 12 over pi, I end up then with 1 equals h squared, squared cubed. And so I know h equals 1. Aha! So down here in my derivative, h equals 1. So if this is 2 and we've got pi over 4 times 1 times dH dt, my answer is going to be 8 over pi, and these are feet per minute. Okay? Yeah, it was a little tricky over here. I mean, you might not see until you get to that place where you say, okay, they gave me that, I'm looking for that, I better figure out how to find that. We want to know what the height is when we're only 1/8 filled. And that meant we needed to find out how much is completely filled, multiply that by 1/8 to find what would be the volume when we were 1/8 filled, and then take that 1/8 filled volume number and set it equal to the volume equation. And that's what I did here. I had 1/8 of the volume equal to our volume equation, and I solved for h. All right, and we get 8 over pi feet per minute. Nice. Okay, 6. 6 is an interesting shadow problem, and I'm kind of happy to say that these were much more popular a while ago than they are now. Okay. So we've got, is that a road? A road runs at right angles to a wall. No, this must be the road. Road, wall. What else do we know? A man approaches the wall at 10 feet per minute. So it says man. And man is approaching the wall at 10 feet per minute. Okay. I see that this distance is called x. There is a lamp on the ground 20 feet from the road. So this is 20 feet, and that little dot is a lamp. Okay. And 40 feet, Alexa off, and 40 feet from the wall. So this distance is 40. Why did I have 3 marks there? Sorry. Everybody just move up. There's the man walking down the road towards the wall. There's the lamp. This distance is 40 feet. That point is the lamp. This distance is 20 feet. Find the rate at which the man's shadow is moving along the wall at the instant when the man is 20 feet from the wall. Okay, so let's call this x, and x equals 20. Now these are two very, very different 20s. This is a constant. This is not changing. This one here, right? This road is always 20 feet from this length at this point. And if we went down, we would always have that 20 feet constant. This person is walking toward the wall. And as they walk toward the wall, we can see that the distance between them and the wall is getting smaller, as is the shadow. Okay, so I think what I want to do is I want to call this shadow. This is a changing quantity. Oh, look, it's already labeled. This is x. This is 40 minus x. So we've got that. So this could be 40 minus x here, because these are the same. And then I see similar triangles, because this is triangle here, from here. So, we've got lots of similar triangle relationships we could use here. When the man is 20 feet from the wall, find the rate at which the man's shadow is moving. So we want to know ds dt when this is 20. This is 20. 40 minus x equals 20. Okay. Do I know how fast the guy is moving? Approaches at 10 feet per minute. Yes, so we said that dx dt is 10. I kind of think it's negative 10 because I think he's getting closer. But not so sure based on this picture right now. Okay, so we're looking for a way to relate x's and s's, shadows and these distances. So what I see here is lots of different similar triangles. So for example, I see these similar triangles. And I could say s is to 20 as this 40 minus x is to, this is x. And so I could do this triangle and this triangle. That's a 20 there. But some people don't see the two small triangles, whether we're talking about these or these. Some people instead see little triangle, big triangle. So little triangle, how about x over 20 equals this is to that, as this whole thing, 40 is to this whole thing, s plus 20. And these don't look the same, but I should, in fact, be able to get the same answer. So before I take the derivative, let's just do multiply here by x and 20, and here by x and 20. I'm going to multiply both sides by the common denominator, and I end up with xs, and here this x cancels with that one. 20 times 40 is 800 minus 20x. Okay, so I got that. Now let's come over here and cross multiply again. 20 times s plus 20. 20 times s plus 20. And so the 20s cancel, and I have x times s plus 20 equals over here 800. And if I distribute, I get x s plus 20x equals 800. Hey, same, right? So it doesn't matter which of the many similar triangle proportional sides relationships I set up, I should pretty much always end up here with this. So let's take the derivative here. Okay, this is product rule. I'm going to have this times the derivative of that with respect to time, plus this times the derivative of that with respect to time, equals the derivative of this is 0, and the derivative of this is minus 20. Be careful, the derivative of this not with respect to x, but the derivative of this with respect to time is going to be dx dt. Now, I got some things with dx dt, so I'm going to move them all to one side of the equation. I'm going to have x ds dt plus s dx dt. Oh, no, 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 I was moving this over. Okay, and so I'm going to have minus s dx dt minus 20 dx dt. Now, I see that I can factor out a dx dt, and so I'm going to have x ds dt equals minus s minus 20 times dx dt. All right, so what do we know? Well, we know the guy is 20 feet from the wall. 40 minus x equals 20. 40 minus what number is 20? Well, that means that's 20 also. So I know then that x must be 20. If this is 20 and this is 40, this has to be 20 too. Also, so I've got 20 ds dt equals s. Yeah, I need to find s. Ooh, and dx dt I was given. So I'm going to have s minus 20 times minus 10. Still got a question mark on that. Minus 10. But what about s? Well, how can I find it? Well, we had a lot of proportions going on, right? We had s is to 20 as 20 is to 20 s. S is to 20 as 20 is to x. X. Okay. Oh, but we figured out that x was 20. So I know s is 20 also. And I guess that should come as no surprise to us in this problem because we've got all those 20s everywhere. So I find out that s equals 20. I put a 20 in here. I get minus 20 minus 20 is minus 40. Minus 40. And don't forget to divide both sides by 20. And it looks like ds dt equals 2. 2. Not 2. 2 times 10, 20. Okay, 20 feet per second. But it's negative. So, did I do a double negative thing here? I mean, I know, but as the guy gets closer, the shadow gets smaller. So, what did I miss? Dx dt. Oh, I see it. Hey, look, they defined this as x. And as guy goes this way, we know he's approaching this intersection, but it's actually this one that we're talking about. X is the distance from here. X gets longer. So my dx dt is actually positive 10. So I want a positive 4. Wow. Frame of reference. Ooh, Heisenberg would be happy. Okay, so there's our tough shadow problem. It reminds me about that one in the textbook where half a second later. Ooh, shudder. Okay, 7. Boy flies kite, which is 100 feet above the ground. Kite. Boy flies kite. Guy's getting to do everything in this. Mr. Kuklo, what is this patriarchal worksheet all about? Why haven't you changed this? Yeah, good question. I'll work on that because that's weird. Oh, I know why the guy is flying the kite. Because the woman is doing the calculus. That's right. Okay. Boy flies kite 100 feet above the ground if the string is pulled out at a rate of 10 feet per second. Well, this is the string. And so we're saying that ds dt is 10 feet per second. which carries the kite horizontally away. The kite is moving this way. So I've got x. I don't want to call this a dx dt, a change in that x value-ness. At what rate is the change of the angle of elevation? What is the change in the angle of elevation when theta equals 30 degrees over 6? Okay, nice. So what are we trying to relate here? It may be hard to sort of see this, but think about this situation, okay? So there we are originally, and then the wind blows and carries the kite to the side, and now we're still at 100 feet high, but this angle has changed, right? It used to be this whole thing, and now it's only this thing. So as we go this way, the kite stays at the same height, but the angle is changing. And that's why they've asked for d theta dt. But curiously, I'm interested in finding a relationship between x 100 and theta. Yeah, so what's my relationship there? It has to be tricky. Tan theta is 100 over x. And that's the equation that I want to take the derivative of. So, with respect to time. So, derivative of tangent is secant squared times, don't forget the derivative of the inside function, d theta dt. That's what we're looking for. Equals, and now the derivative of this, and you might want to write it like that. So you have negative 100 x to the minus 2. Don't forget dx dt. You have to take the derivative of that inside function with respect to time. Okay, now what do we know? We know that ds dt is 10. Whoa, Mr. Googla, what, but 10, where does 10 go? Yeah, that's a thing, isn't it? There's no s here. Wow, maybe I didn't want to do tangent. I thought tangent was nifty, though, because I had this constant. But, yeah, I need string. I need to use ds dt. So, what can I say about ds dt? Well, well, I think there's no getting around it. I need to use the string. So, close that one. And I'm not told. Yeah, I'm not told about the rate of change. So I'm not going to do that. I'm going to acknowledge that the kite moves sideways. I'm going to acknowledge that there's more string here than there was originally. And I'm going to acknowledge that this angle, theta, that's small. So I'm relating those things. I'm relating theta. And now I see sine theta equals 100 over s. Cosine theta, d theta dt equals negative 100 s squared. Don't forget the derivative of s with respect to time. Okay. We know theta equals 30 degrees or pi over 6. So cosine of pi over 6. Cosine of pi over 6 is root 3 over 2 times d theta dt equals ds dt 10 negative 100. What about s? How long is that? Well, if this is 30 degrees, I could use 36 to 90 techniques to find s. Short leg. Is that short leg? Yes, because that would be 60, and that would be long leg. This would be 3. This would be. So with my 30, 60, 90 shortcuts, my short leg is 100, and my hypotenuse is always twice the short leg when I take 60, 90. So I can find s that way. Or I can say, well, I know that the sine of theta equals 100 over s. And our theta is pi over 6. Sine of pi over 6 equals 100 over s. Sine of pi over 6 is 1/2. And so if I cross multiply, I get 200 equals s. So I could also find s that way. I do need to plug that s in. We came up with s equals 200, so this is going to be 200 squared. And I can need a little more space, some cars here. And I get that root 3 over 2 theta 2 equals negative 1,000. I still have more space because I'm going for ds dt. Root 3 over 2 theta dt equals negative 1,000 over 200 squared ds dt. All right, what are we looking for? Oh wait, ds dt is 10, and that's part of that 1,000. I'm looking for d theta dt, so I'm going to multiply both sides by the reciprocal. Those cancel. Cancel with that. I got 10 over 200. And 1 over 20. 3. Or negative 3 over 60. Let's see. Negative 3 over 60. Yep. And, negative root 3 over 60. Remember, these are radians. And our time was seconds, 10 feet per second. So, and so it looks like the angle is getting smaller by root 3 radians every 60 seconds. Okay, when theta equals pi over 6. All right, last problem. Revolving light is located 5 miles from shore. This is the light. This is shore. And this is 5 miles. Constant velocity. Kind of want to think about d theta dt. An angular velocity. Yeah, constant angular velocity. With what velocity does the light revolve? Oh, I am looking for d theta dt. If the spot of light moves along the shore, spot of light moves along the shore at a rate of 15 miles per minute. So if this distance is x, I can say that dx dt is 15 miles per second. 15 miles per minute. That's a little more believable. The beam makes an angle of 60 degrees with the shoreline. Hey, watch out for that. Because while this is my theta, the angle that the light is turning through, they're giving me that this is 60 degrees. This is not 60 degrees. The angle with the shore is 60 degrees. So when the angle of the shore is 60, when theta equals 30 degrees. Okay, so now I think I do want a tangent equation because I want to relate this stuff and this stuff with this angle. So tangent theta equals x over 5. Take the derivative with respect to time. I'm going to get secant squared theta d theta dt. And here, no, not quotient rule, it's 1/5 times x. It's just 1/5 times dx dt. We know dx dt is 15, so I'm going to have 1/5 times 15. And over here, we know that this is 60, so this must be 30, and 30 degrees is pi over 6. So I want secant of pi over 6 squared. Okay, so secant of pi over 6. Well, cosine of pi over 6 is root 3 over 2. Secant would be 2 over root 3. And then I'm squaring, so I get 4 over 3. So I have 4 over 3 d theta dt. Well, I want to get d theta dt by itself, so I'm going to multiply by 3 over 4. So d theta dt equals, oops, I'm canceling, 9 over 4. 9 over 4, and those are thetas, so that's radians. And this was minutes on the bottom. And there's our problem, okay? You know, the cool thing about these videos is if that went way too fast for you, you know, you could watch it again. And this time you could, you know, write down some questions and ask me some questions. And I think that would be fabulous. So I look forward to your questions. Have a wonderful day, everyone.